Hey folks, I am rewriting my cloud native personal finance app to a Woco native desktop and mobile apps for each platform. With that, I started with the macOS and iOS apps, and currently I have finished the macOS initial version 1 app and am testing and refactoring it. But at this point, I think it's going to be possible to make this kind of video where I share my impressions of writing a modern macOS app, because I've done it before, but it's been a while and it was in very old versions of macOS with Objective-C. And I just want to share my thoughts on some aspects of Swift, SwiftUI, native Mac apps. Let me first show you the app so that you know what I'm talking about and what I've built. Budget Warden looks like this. It's a native Mac app. And this welcome screen opens when you open the application. Budgets in Budget Warden are just files, and you have a vault, which is just a folder that you can configure to either be on your drive or in iCloud. And as budgets are a file, you can create one and use templates for it or a previous budget. When you open a budget, this is essentially what you get. The point of the application is to plan your personal finances for some period. In this case, I've made my budget to be called May 2026. And here you use the letter budgeting methodology where you split your income, especially your outflow, to a couple of categories where you plan an amount for each category and then you track the actuals. When you create categories here, you enter the planned amount. Then the actual gets updated when you create transactions, which is right here, and transactions each go into a category and get reflected in your actuals so that you can track if for certain categories you're on track with your spending for the period you're interested in. We also have reporting in two steps. We have reporting in two views, actually. In this view, the main budget view, we have a reporting, essentially glimpse reporting, quick reporting with only a few things. Now for advanced reporting, I have a whole page here with many different breakdowns that might be interesting. And here you can again toggle planned and actual. And while you're in a budget, you can switch to other budgets from your vault or create another one. And things like that. I mean, this is the essence of the app. What's interesting is this is a fully native app. It uses no custom components. Essentially, nothing is custom drawn. Everything is native SwiftUI, including a table. All of the charts are native charts and native components for navigation, views, a toolbar, etc. So that's the thinking. Now let's get into some technical details. Starting with Swift. It can be a very large topic. As any programming language, it has a lot of features and a lot of things to talk about. I will talk from my perspective and for the specific use cases of Apple's application programming, which is primarily what Swift is aimed at. In my opinion, Swift is very similar to Rust in terms of not just philosophically, but syntactically as well. A lot of keywords are shared. With that in mind, this is just my opinion, Swift seems less consistent and it seems to have more keywords in general and be a larger surface to learn. That is not I haven't measured if it's consistent. I don't have this consistency metric, or I haven't measured if Rust is a larger language by a number of keywords or concepts that you have to learn. It seems that way for the tasks I use both languages for. And I think that seems that way because Rust is a general purpose programming language that is taken very seriously by the foundation to keep lean consistent. I don't know if I can use the word lean for Rust actually, but it's meant to be a general purpose programming language for many things and all things. Swift is Apple's internal language, and they don't seem to be afraid to add features to it to solve their problems. And that, you can feel that when you use it. There are things that I would call opinionated in terms of language design. I'm not saying that's bad, good, it's just how it is, in my opinion, right now. Now, with that aside, Generally, Swift is a modern programming language, and it's one of the better modern programming languages that I've experienced. So in that aspect, you have probably worked with a lot worse, and you will generally, I think, consider it a good programming language, productive programming language to work in, which is enough in most cases. Now, let's talk about memory management. Swift, by default, Swift doesn't expect manual memory management. I don't know if it supports it. I guess it supports manual memory management if you want to use it, if you want to do it, and you can write C and interrupt it. But by default, it manages memory, not with a garbage collector, but with automatic reference counting, ARC. I guess most of you know what ARC is, but here's an example for those of you that don't. Let's say we have some object, a budget, and we create one object, one budget object with B1, and we have a reference. B1 is a reference to that object somewhere in memory. And that reference will hold a counter, literally, of things that point to it. This is what automatic reference counting is. So that if we point a second variable, B2, pointer, let's call it, to B1, to the same object in memory as B1, the reference count of that object's reference will go to 2. And the point of that reference count is that later, as we unassign these objects and they stop pointing to that memory, the object knows that it can destroy itself. That's the point, knowing when to destroy yourself. This an alternative to this for automatic memory management is a garbage collector, which would be a software that runs and constantly checks, not constantly, it checks in periods what memory is unreachable and cleans it up. I like automatic reference counting for these use cases, graphical user interface apps, more than a garbage collector, because automatic reference counting is more predictable. You know when the object will be destroyed, when the reference count goes to 0, and you control that. Like, you can control that if you want. With a garbage collector, poses can be unpredictable, which in graphical apps can mean frame drops, unpleasant things in general. And the experience of both is similar in terms of developer. A managed memory language, it's sort of similar in most cases. So that's the memory situation. Now, in terms of the other interesting thing and relevant thing when it comes to graphical user interface apps is error handling. And I hate the classical try-catch exception handling that C++ used to have, C# and Java had, because it's unpredictable, hidden. Performance is usually very bad with these solutions. I don't know if in modern times they've managed to make them faster, but I don't care because it's just unpleasant to use and unsafe, I would consider it, because it's so hidden away. Like, you have some functions that throw things, other functions that don't throw things, and I don't like that. Thankfully, Swift has a lot of they support different kinds of exception and error handling. And what I lean towards using is to always, in functions that could fail, return a result object. Like in Rust, similar thing, because I'm used to it from Rust and other languages, and I like it because it's explicit and you have to handle all situations, even if it requires a little bit more typing. And this is an example from the code base. In code budget takes a budget struct and returns JSON. And I return a result here. You can see I handle possible failure points, and I return failure, which is a BW error in these cases. BW error is a custom error type that supports some user-friendly message and the underlying error, which I then walk and I display to the user. And in the case of success, it just returns the JSON. And how I use this actual function in practice is sort of like this. Encode budget is a part of BW codec. So I store a response, JSON res, and I use a switch statement to handle all possible cases. A switch statement in Swift is similar to a match statement in Rust in that you have to handle all possible exit points. It's not like a switch statement in C, for example, where you can handle whatever you want. Even if it takes a little bit more typing, I like it because it's explicit, and that's exactly what I want with error handling. I want to handle all cases that I can find and think of and handle them explicitly so that everything is transparent. The next important pillar of graphical user interface programming, which I think is very relevant, is asynchronous programming, multithreading. And that's relevant for desktop and mobile apps because when you build a graphical app, you usually have what I would call a main thread. So the main running program that draws, the main thread that draws the user interface, creates the animations, displays things graphically. And you usually don't want to block that ever because it would freeze the app and it's an unpleasant experience, at least in a modern app. That's the expectation of most users, that UI will remain responsive while tasks are happening and indicate somehow that something is happening. And that's especially true for tasks that run longer. With some tasks that are a millisecond, for example, you can probably get away with synchronously blocking the main thread, but long-running tasks are unacceptable to run on the main thread. So your graphical user interface app has to be multi-threaded in some way, and you usually in modern languages don't have to always spawn an entire thread for a task. They have these virtual threads, asynchronous tasks, asynchronous programming, JavaScript promises, however they are called. They're usually tasks that run in parallel in usually separate threads. But like in most cases, there would be an asynchronous runtime that would spawn multiple, like say 2 threads and run a lot more tasks on these 2 threads and do it intelligently. Now, Swift supports this kind of thing. And here's an example from the actual app. This is my welcome window, which you saw before, and that window needs to load the budgets from Vault, which is a file system operation that can take longer. And this is the actual view, but in the view, you initiate a task from the store that is awaited. It's Vault budgets from Vault. That task happens asynchronously now with Swift's task runner, which is the asynchronous invocation runtime, let's say. And tasks are one part of the equation. This is how you invoke asynchronous functions from your graphical user interfaces. The other thing that's important is that when you have asynchronous tasks, you need to handle joining and them accessing the same objects at the same time, leading to unpredictable results, which is the classical multi-threading error, which is why a mutex exists and stuff like that. Well, Swift has this notion of actors. And an actor, this is my BW Vault, let's call it a class. It's an actor. An actor is a similar thing to a class. And BW Vault does a couple of things that shouldn't happen on the main thread, like read budgets from Vault, which is a folder, save a new file, remove a file. So these operations can take longer. They are file system operations. And they should happen on a separate thread. Having this as an actor instead of a class means that by default, it's a separate entity, and Swift ensures some safety rules about modification across threads. A classical example for this is if you have some, say, counter in your main thread, and you have to increment it after doing some long-running task. That if you spawn 2 of these tasks in parallel, you don't know which one would increment the counter at which time. If you want them to have a predictable result and to be able to essentially walk the result object until while one actor is working with that object, you need some kind of mechanism. And actors are essentially Swift's mechanism to ensure that concurrent safety between asynchronous contexts. So these are the main two, concepts I had to get familiar with when dealing with multithreading, an actor and tasks. There are other ways to do multithreading in Swift. Again, but this is the practical notion of what I needed to use in my application. The other part of a graphic user interface app is, of course, drawing the interface. And SwiftUI, as a part of Swift, sort of, I guess, SwiftUI is the declarative UI language which you use to define your actual user interface. And SwiftUI supports everything you expect to have. It's built into Swift, very tightly integrated with Swift, so you don't feel like you're writing a separate markup language or something like that. Here's an example of a component. It supports components as well as views, and they are a very similar thing. I mean, views are composed of components that end up on a scene, so-called scene, which is like, let's say, a page. And this is one of my components, the sidebar view, that shows the three buttons. And here we see a couple of things. Each view has a body, and the body is what is rendered with that component. And here I use a list, which is a native SwiftUI component, and show sidebar buttons. Sidebar button, you see, is a private function that I use sort of like this static inline component within a view. And that's a convenient way to use a component that to just separate a small component that's only for this file, which I like. And you pretty much chain properties and modifier, let's call them functions, on each of the components, which I don't particularly like because it gets a little bit longer and hard to read. But in pretty much any declarative UI, you need to have some kind of something like this. And this is their approach. I wouldn't call it bad or exceptionally good, but it's okay and does the job. Now, the other important features related to UI work and reviews are state. State variables are supported by default. You can think of this like React, like Elm architecture UI. So you essentially have state variables which use the observer pattern to update user interface as they change. And you define them very easily, just denote them with state. And that's it. From that point onward, they would affect rendering. And the other good thing, good or bad thing, I don't know, you have dependency injection, some sort of dependency injection with environment objects. It allows you to set some environment objects, context, dependency injection things, so that you don't need to probe drill. You don't need to drill and pass your store or Windows Store, my two global state objects in this case, to every component down the chain. I want to talk about my previous video when I said I will rewrite the app. I mentioned I plan to use a shared C core for the core budgeting functionality, business logic, and all of that, and just have the user interface layer in the native platforms so that I can reuse that core on Windows, iOS, Android, etc. And I decided to write it in C so that it's easy to reuse and it will be supported everywhere. I went against that. And this is an entirely Swift app, and the other apps will be written when the Windows app in C++, the Android app in Kotlin, and so on. I decided against that because there were performance issues with that, which are not very easy to solve. For example, strings. With C, you do have C strings, and you need to write some kind of string view dynamic string. And when you do that, you need to convert that to a Swift string at some point, somewhere. Ideally, you would want to not mirror the logic in Swift, which makes the C core useless. And the good thing about C core is you can manage memory efficiently there with an arena. You can be precise. But the reality is that has performance penalties because each string has to be converted if you want to use it directly in the UI inefficiently and while user interface is drawing, which is a huge performance penalty. So the solution to that would, in using C core, would be to have the structs in Swift and the structs in C. And data and wrapper functions in Swift maybe, or at least the structs mirroring the data. And that makes the core for this specific app useless, largely because file system operations also need to happen in Swift to use the native first-class APIs. And even the application was doing something more, which was significant, I would do this approach. Write a core in C, Zik, Rust, whatever is appropriate. But for this specific app, the core wasn't carrying its weight, essentially. It was introducing complexity, which was not necessary. And bringing it into the Swift code base reduced the surface of the code significantly, improved the performance, and that was my decision. To ensure consistency between the desktop applications, I would use the budget file format as a consistent baseline. And I will make sure they all mirror their logic perfectly at all times. That is my responsibility. Now, let's talk about dev environment. I'll show you what I used to actually develop this. I do like simplicity, and I use tmux, Neovim as my text editor, and tmux to have a couple of terminal sessions and navigate quickly between them. I also frequently open a side view, like right here, a split screen, so that I can see two files open and refactor something. That's frequent. Now, to work on the app, this is usually what I use, just my text editor. To build and run, I have two scripts right here in the macOS folder. I have a build.sh script that builds the project with Xcode. This is what I use to check for errors. And I have a run script that builds and runs the app. And that's what I use most of the time. I just, let me quit Neovim. I have two terminal tabs. I write code. I go here. I run. Let me go. I run the app with the run shell script. I do whatever I do. That's it. And admittedly, in some cases, you need debugging, or I need to edit the Xcode project properties. For these cases, I have Xcode open in another desktop, and I would debug there. I would use it just as my debugger and for project configuration, because a lot of macOS metadata about the app is configured easily through Xcode. I mean, that's my setup. Very simple, single repository, very handmade hero style, I guess. Now, testing, I only have end-to-end tests at this point, not unit tests. I will add unit tests before I release the app. I'm working on tests right now and started with end-to-end testing, user interface automation testing. And I use Apple's native, I think, Xcode test framework. And I'll show you how I use that right now. This is, I currently have only one file, and this defines a couple of tests. It's getting a little bit longer, but whatever. And this is similar to something like Playwright. You essentially say, find this button, wait, click it, expect that text to exist, stuff like that. And to run these, I use the test runner in Xcode, and I just run the test from right here. And this is well integrated with Xcode, as you would expect in an IDE. It will build the project, and in a couple of seconds, it would ask me to allow it to take control of my operating system and automate. There we go. I enter my password to allow XCTest, And you see this automation running label, and the tests will begin working in a bit. There we go. And this allows me to do end-to-end testing. There's also a unit testing framework in Swift, which I'll use later to do that, to integrate unit tests as well and have testing at that level. But end-to-end is what I started with to ensure baseline reliability while I am working. Admittedly, that might be the other way around. I'm not religious about testing. In this case, that's how I decided to go along with it. Finally, I want to mention, even though the app will be a one-time purchase app, cheap app like for $2.99 or whatever on the App Store, I wanted to have the source available for learning, and because I share it on YouTube to people to learn and share experience. So I figured out how to do a source available license, which allows you to read the source code, learn from it, experiment with it, but not use the actual app. The license permits just learning from the source code and reading it, a source available license. So the code is available on GitHub. It's linked in the description. It's currently called Budget Warden Next because I have a Budget Warden repository for the cloud app. Later on, it will be renamed, but you can explore it and check it out. And that's what I have to share about this for now. I am still working on testing, ensuring some reliability, and refactoring heavily. The code is not perfect. I do prefer larger files by default, but I want them to be organized larger files. And I have a lot of refactoring to do and quality control in terms of testing before I release. I also want to test older macOS, stuff like that. But yeah, these are my impressions from modern macOS development and Swift. And I thought I'd share them because I find videos like this cool. A first-hand experience of what a person thinks is most important after finishing a real project. Share your thoughts. I'm not an expert in this in any case. I haven't done a macOS app in years. And this is the first time I've touched Swift practically, instead of just taking a look at a few tutorials. So yeah, share your thoughts. Look at the source code. If you have recommendations, you're welcome to give them to me, or tell me where I've messed up. Yeah, if you built something, share it in the comments. I'm also interested in that. So yeah, that's that. As always, stay curious and take care.